Okay, back to pre-calculus or calculus. We're in section 3.1. This will be part B. So we left off on notation, alternate method for definition of derivative. We're going to start talking about the relationships between the graphs of derivatives and their original functions, or between f and f prime. So what you're actually going to need to be able to do is you're going to be able to give a rough construction of the graph of f if given the graph of f prime, or vice versa. If given the graph of f, give a rough construction of the graph of f prime. So if you remember, derivatives are just these slopes, right? So if we look at the graph the graph of the function f, maybe I'll just draw one. Yep, that's what we'll do. We'll draw one. So let's kind of simulate the graph of this function. Kind of does this and then does that, right? This is kind of no particular function. If we look at the slopes, we can estimate the slopes at various points on the graph of the function. This will be f of x, and we can use that to give us the graph of f prime of x. All right. Now, the main thing you want to look at is if we trace this slope, right? If you think of it like a roller coaster, we're going up, right? That's a really, really high slope. That's steep, or not really high, but it's a steep slope, right? So it's definitely bigger than the number 1, right? Because our rise is bigger than our run. So as we go up, our slope is positive, right? And then as we start turning, the slope gets smaller and smaller, right? Until we get to right around here, right? If we think of the markers tracing the slope, we get to right here, like the roller coaster, and there's no slope anymore. There's that point on the roller coaster where you're staring straight at the horizon. That's where we can estimate our slope, because we can estimate right at all of our curves, our slope is equal to 0. All right, so we can see that at this turn, and then we can see it starts turning down, and now our slope becomes negative values, right? So we've got negative, so up here we've got positive numbers, then here we've got negative numbers until we get back to here, where our slope is 0 again, right? So we got positive numbers, negative numbers, 0, and then we'll go back to positive numbers, right? So using that knowledge, we can kind of guesstimate the graph of our slope, and then also using the really rough estimates of the slope. We'll just pick like 2 points from here to here. We'll just do an average slope, so it won't be perfect slope at a curve, but we'll do a rate of change, right? So a traditional slope. So we've got a rise of 1, 2, 3, 4, 5 over a run of 2. So right here, that'll be about like 5 halves, right? So at the point, actually at the point 1, we got a rise of 3 over 1, right? So we'll just estimate the slope right around here. We'll call that one, that's 3 over 1. So we got a slope of 3 here. We'll make that positive 3. And then over here we got a slope of about positive 2, right? And then the slope tapers off, okay? And then can't really figure out what it is at 0. But then we'll go down here and we'll go to 1. And I'm still estimating here. So we'll estimate that at 1 the slope is about 3, right? And then at 2 the slope is about 2, and then we know that at this point 3 the slope is definitely 0, right? So that's what we're seeing here. Maybe I gotta zoom out more. Oh wait, my zoom on my camera is too close. Okay, right. So we can kind of see the curves. They go in opposite directions. As this one rises, the derivative falls, right? As this one turns, the derivative crosses the x-axis. All right, so that's a very important point. At every single time your original function turns, your derivative is going to cross the x-axis. They're like these zeros, or the roots of the function, which is really interesting, right? So we can see here at 3 we've got about 0, and then we can see over here at 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 we've got 0 again. So 9, we've got another point of 0, which means from here to here it's going to kind of dip, right? Which is what we see. It's in the negatives, okay? So if we guesstimate from here to about here, that looks like about negative 1 over 3, or negative 1/3, right? Rise of 1 over 3, yeah, so about negative 1/3. So I can go over here, and at this point, what is this, 6.6, I'm about at negative 1/3, right? So even though it's negative, it's not really high negative numbers. And then we go from here to here, that looks more like a negative 3. So yeah, right here we're at about negative 3, right? So the graph of the derivative is a little funky, right? And then we can just kind of loosely connect these lines. right, to get our graph of our derivative. Okay, so the main thing here is catch the zeros and then do some rough estimates on what you think the slopes are at these areas, and they can be as rough as I just did here, and that's how we can kind of figure out the graph of f prime of x, and vice versa. If I had the graph of f prime of x, I would know that these zeros, these are going to be curves, right? And then as this is, whenever f prime of x is in the negatives, well, that's a downhill, right? So it's going to be going downhill, and then if it's positive, well, that's going to be an uphill climb, right? So we can use that knowledge to help us sketch the graphs of the prime and the original functions. So that's the first bit of knowledge on this video. Now let's keep going. We'll go talk about okay, so here's some interesting stuff. When we have linear equations, we're going to have some discontinuities, or some removable discontinuities, or some jump discontinuities. Let's zoom in so I can keep my focus. All right. So if they give us the graph of this derivative, so what they've done in this problem is they gave us the graph of the derivative of function f of x, and they want us to graph the function. So what we see here is that whenever the derivative is a straight line, right, the slope of this is essentially 0. Or sorry, no, not 0. Sorry, 0 would be right there, since this is so they're saying the slope of this is -1, right? So the slope is not changing. When the slope is a horizontal line, that means you've got a linear slope that does not change. There's no curve in the slope. And then over here, we've got another horizontal line of slope of +2. So there's just a straight slope there. And whenever that happens, what we're showing us is the slope of straight lines. So whenever your derivative function has no curve to it, then neither does your original function. All right. Whereas you can see over here in this function, you gotta zoom out again. Okay. In this function, you can see where the curve kind of starts to bottom out, and of the derivative, the slope starts to be constant. We can see that this slope was really, really similar over that whole interval, right? It's almost like a straight line from those points, right? And that's what we're seeing on the derivative slope. And then right here, as the curve bends very fast, you see that drastic change in the derivative. Okay? So I think that's it for graphing f from f prime and vice versa. Yep, graphing derivative data, we just talked about that. Okay, estimating the probability of shared birthdays. Actually, you know what? I don't think nope. I don't believe we're using that. Nope, that's just a cool trick. All right, so we're going to be talking about one-sided derivatives. So just the same way that limits can be one-sided, derivatives can also be one-sided. So remember, if a limit seems to approach different numbers, right, on the left and right-hand sides, then we'd say no derivative, I'm getting derivative and limit confused. All right, so if we have a limit where it approaches different numbers from left and right sides, we'd say no limit exists at that exact point, right? So let's go ahead and draw this. We'll erase the f prime. So let's say we've got a function like this, and then like that, right? So if we approach from the right hand side, it looks like the limit's going to be 0. If we approach from the left hand side, it looks like this limit's going to be +4, right? So what we could say is that a left-handed limit exists, right? So the limit at -0 exists. We could say the limit at at 0, sorry, not -0, 0 from the left hand and 0 from the right hand. We say that those both exist, but we would say that the limit at 0 does not exist. The same is true with derivatives, okay? So if you remember, we use the traditional definition of derivatives, right? This f of x plus h minus f of x over h. If we see that it approaches from the left-hand side and it has a derivative of 0, then we can say the left-hand derivative is 0, right? And then if we say approaches from the right-hand side, but now that the derivative is 2, then we would say that the derivative at 0 does not exist, but it does in fact have a right hand and a left hand derivative, right? Now this is what we see with piecewise functions. This piecewise function, the left side being the graph of x squared, the right side being a linear graph y equals 2x, right? So with piecewise functions, often what you'll have is derivatives at the point not existing, but right and left hand derivatives existing. Okay, I don't think I need to go over the notation for that. It's just the f of x plus h. It's just when you plug it in, you'll be using the left or right hand based on these piecewise function formulas. And that's it for 3.1. All right, so this video is much shorter. That's hopefully a good thing for you guys. If you have any questions, let me know on the school website, and I will see you in class.